Okay, this will be the additional video on our course, a continuation of the polymer synthesis. This is the part 3 of our polymer synthesis in our course, and we are going to focus on the chain growth polymerizations. So this will be our outline. We have several agenda, but I think for this video, we are going to focus on the first two, which is the definition and introduction of chain group polymerizations, and also the chemistry of conventional radical polymerization or chain group polymerizations. Okay, so we first going to see the definitions on the chain group polymerizations. So I think we can describe the chain growth as we can describe this as a basketball. So imagine you have a basketball in your hand and you would like to play with your friends. And how to play basketball in this case is, imagine that you can only hold the ball for a few seconds before you pass the ball. So to make it works, then whenever perhaps 1 or 2 seconds you need to pass the ball to your friends, and maybe if it is in the class, imagine that all the students will get the ball, and that is actually how we could imagine how the chain will be in the chain growth polymerization. So imagine that this first ball here, you need to pass from here, go here, passing through, and imagine that this is going to be a link. Okay, this is going to be a link, and it will be a polymer. And imagine that every student is the monomer. So you need to pass through this ball here, there, right? So this is what we call the high energetic species. The ball is actually our radical, which has energetic species in thermodynamics perspective. Okay. So another thing is, to make this happen, this radical species works really well in fine ion monomers. Okay, which means it has the double bond. Okay, it works well with this double bonds. Okay. Okay, and then we could see that in another perspective, if we could see the free radical, where is the electrons located? If we could imagine the forms, usually if we read the textbook, this the picture on the right one, the third one, this is mostly we are going to see in the books, right? This one. But actually, in terms of the locations, this first picture is the best way to describe. Okay, this means that this radical is on p orbital. Okay, so you imagine that electrons, they are having their own orbits, right? And there are many ways the electron can fill up the orbits, right? And especially for this case, the radical is actually on the p orbital, which means that it's not on the backbone of the monomer itself. It means the backbone means the bonding is not on the major chain, but it is on the side chain. Okay, we can say something like that. Okay, it means that this radical is really reactive. It's really reactive, and it easily getting attracted to, especially the carbon on the double bonds a monomer or the final monomer. Okay, so that's how it goes, and this is the idea. Okay, how we could prepare the monomer, and then usually we start with the initiator I, which means that is the radicals that will be going to attract or going to be going through the monomer that has this double bond. It can work either with the first case here. Let me just add here. It can work with this, or it can work with this. Okay, we can have this too, because they are basically similar similar steps, similar process. So if we start from here, then imagine that the bonds will broken. Let me the bonds will broken. I think let me use the let me go back and okay. So let me start from here. Okay. Now this, let me check first. This will be having the electrons. Okay. So after the initiators broken the double bonds, it becomes destabilized, and then it will kick out one electron. That is going to be the next unpaired electron, and this is also the reactive electrons. It makes this monomer species will be highly reactive, and then it will plus another double bond, which at the next process, this will links up, and then it will kicks another electrons. Okay. So this part here, this CC, this will be going to be repeated more and more and becoming a polymer. Now, if we add the uh, the energy, how much energy we need, this CC we need. This is sigma bond. It's on the backbone of the molecules. It's around 348 kilojoule per mole. And if we have the this pi bond, is around 614 kilojoule per mole. And then we have here this C, C, and C. You see that there are three bonds, three sigma bond, which is 1044 kilojoule per mole. Imagine we have first is starting out as a 1 sigma bond, and now we have 3 sigma bond. Okay, so this reactions is exothermic or spontaneous reactions. Okay, and next is we're going to see that some steps and processes. We start with the initiation. The idea is to generate the radical species, and it forms an active center or an active chain end. And then the next part will be extend the chain by adding more monomer. We call the propagation steps. And at the very end, it is termination, which we need to remove the radical sites and to end the polymerizations. Or we could go for a chain transfer. We can transfer the radical into the other chain, okay, from the chain end to the new chain. Okay. Now the next part will be about the chemistry of conventional free radical, or perhaps um, the difference between the the radical polymerizations and the step growth polymerizations. We haven't yet really thought about that, but let me give you some illustrations. Okay, so the step growth, the molecular weight will be slowly takes time as the conversion increasing, as the P increase, right? But chain growth at the initial stage, at the early stages, is going to be like that. This is chain growth, or maybe it's better to make it. Okay. So as early as the stage in the beginning, the chain growth already has a high molecular weight. So in terms of time, chain growth has, I think, fastest in many ways compared to the step growth. But the molecular weight that is as a result from the chain growth is not as high as the step growth. Okay, because step growth, it can make up 99.5% easily, while the chain growth for 95%, it's not so easy, okay, to get the 95. We're going to see later the summary on chain growth and step growth. But let me start with the radical polymerization or chain group polymerizations, which we need to prepare from the monomer that has double bonds, or we call the final monomers, like this or this. Okay, the difference is we can exchange the X with some other molecules. Okay, we can get for other carbon, or we could get the X for benzene, for example, ring structure that has um, sterically more, having more spaces in the structure. Maybe if we need the polymer to be strong, like stiff and strong, then we need a benzene on that X. Okay, anyway, let's go for the initiation part. Okay, so the initiation, so basically we say initiator need to be prepared, and we need to make it into initiator that has free radical. Okay, so we need to form a free radicals from the initiator, and if we add this initiator that has unpaired electron, then we start the polymerizations. Okay, so we start up by adding this into our double bond or the final monomers, and then we get this to become active, and this active chain end will connect with other final monomer, which then create another chain end, and this will be connected, and we have or maybe this is still double bond, still single bond. And the way we see this part is they are going to repeat more and more and more as we add more monomer. And how the monomer added is actually, if you can imagine how much time we need, is actually in a fraction of seconds, every part of the monomer. So it's really, really fast. And one important requirement is the initiator. The bonds need to be easily broken. Okay, to make our polymerizations stuff easier. And how to generate, how to broke these bonds, we can have several methods. We can have it using thermal, using UV light, or using a redox process in chemistry. This is the idea is to generate this unpaired electron. Okay, now let's see how it goes one by one. Okay, so the first principle within this initiation process is the first thing is we need to make sure that it can be easily broken down, or we call it homolysis. And then the second principle will be the single electron transfer process. So only one electron or unpaired electron that will be transferred, because that is the one that has the high energy level. Okay, so the first one here is the peroxide, and this is the diazo molecules. And this too is the common initiator in the chain group polymerizations. Okay. Okay, I think we can go for the next one. And this is for thermal treatment. For example, we have benzoyl peroxide, butyl hydroperoxide, azobis, isobutylonitrile, the diazo, and all of this they have a similar process, which is we are going um, to cut the initiator molecules. So we have a homolysis here, we have here, and we have this is the um, cutting with that. Okay, so the first one you get into two benzoyl radicals, and this is going to have a butoxy radical, and oh, this is not true. This is not true. It's supposed to be here. Okay, and hydroxy radical, and this becomes this cyanopropyl radicals and that product as a nitrogen. But the idea is we cut off the initiator molecules. Okay, we have the homolysis. Okay, using the thermal treatment. This is, I think, common initiator for thermal treatment. And this is for the UV light. The idea is still the same. You see that the benzophenone, we give lights, and then it breaks the benzyl radical and phenyl radical, and then benzoyl alkyl ether we can cut, and then having a benzyl radical and alkoxybenzyl radical. So again, homolysis. Okay, and I think I don't want to explain really much here, but I think I hope you get the idea that the we need to cut through the initiator, the bonds in the initiator, so that we can have the our radicals. Okay. Okay. The other process is the redox process. Okay. So you see this, we have the cumyl hydroperoxide and the ferrous ion, and within this, we need to make sure that this ferrous ion, we can say the electron transfer from to hydroperoxide. And we have this radical. Same thing with the second one. we are going to have a transfer from here, from the bisulfite ion, so that we have the bisulfite radical. Okay. Okay. Now there are two um, two modes that can happen in initiation for how the active center is formed or created. The first mode, we say this one. The first mode is this. Okay, that one, the top one. So the radical will be here, and this will be the X molecule if this X. And the second mode, X will be in the middle, and radical still there. Okay. So the difference is the positions of X, okay, which is going to be determined by what kind of molecule X will be. So if we use a lead X um, benzene, okay, so we have H, and we have benzene. Imagine we have the structure as a in terms of the molecule. Remember that the the electrons that we have, the unpaired electrons, is going to be in this side here, right? Between those, okay, between those orbitals, still in the p orbital, right? Electron in p orbital, okay. And then imagine this benzene is really large, right? Compared to the um, only the single carbon atom, right? This benzene, it has 6 carbons, so it should be huge compared to the single carbon, which means uh, the electrons will prefer, okay, will prefer, or how to locate the electrons, because there are only few spaces available because of the huge structure by benzene. Okay, so the only way that um, the localization, so let me write here, this will be the localization of electron density. So because we need to delocalize, and because of that, it will lowering the level of the energy. And because we have low energy, it means that stability will be increased, okay? So because of the structure of the benzene, that is going to be affecting the location of the electron, how they are going to dense itself, okay? It will makes the stability increasing. So that's why if we can have X as a benzene, then they will prefer the first modes. Okay, the first modes. So it means that this R attack here, and then it will. So it can take the electrons, kick away, and then put here, because we have so big structure here that it won't go that way. Okay, it won't go that way. But in the second mode, the X is not as big as the benzene. So this bonds. So if it's not benzene, this bond can also be affected, and then this could be having another H, and then this could be okay. It could be happen that way. So the X will be in the it move away to the other carbon. Okay. Okay. Anyway, I will write maybe some notes here that you can take as a uh, perhaps example or some definition. So let me write here more space or X at unsubstituted N. Okay. And there will be overlapping of the orbitals because X is so huge. Let me move my face here. Between X and the p orbitals of electron or radicals. Okay. Or if you read my notes here, the mode 1 it's dominant because the attack at methylene is less sterically hindered. Okay, so that's why it choose the uh, the mode 1 because in the structure of the benzene it will overlap the orbitals. So we say it is energetically stable. Why? We say that it will be stable because uh, we can have the localization of the electron density. Okay, it will overlap the orbitals between the methylene and the p orbital of the radicals. Okay, yeah, here we have it overlaps between methylene and p orbital, and it will create the localization of electron density. Okay. Okay, I think we can move on. Now we have another process which is we call the propagations. I think as we can see, based on the modes, we can see as it's actually the same as a previous initiation. We can have 1 and 2. It will have a domination because of the same reason we previously mentioned. If the axis is going to be maybe huge structure like benzene, it will prefer the mode 1. We can see it will be head to tail addition. But if X is maybe smaller molecules, it can be head to head addition. Okay. 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 And then the third part will be the terminations. And terminations, we can have two modes in termination. So the idea of termination is basically we need to make sure that the active center or the radical is going to be destroyed and stop. Okay, so the propagation will stop. Okay, so no more adding monomer. Okay, so we are going to stop the polymerizations, which means it will depend on how we remove the radicals. And how to remove the radicals is basically, we have the first method we call the recombinations, which basically, if you see the picture, that the radicals, they are going to combine, which means that they are going to take some bonding together, and thus it will stop the polymerizations. Okay. And in the final monomers, recombination will be a dominant. Okay. For the CC double bond CC, okay, it will be dominant. Or if we use the, if we have the alpha methyl group, okay, if it involves that group, then we can have this mode which we call the disproportionations. So disproportionations is because the alpha methyl group, it provides additional CH bonds that the H can be released, can be extracted. Okay. Now if you see this, okay, maybe if you can see that this could be this part here, okay, that is, I think, the one that has the H atom that can be released, so that this H, it can go for the so it, I mean, right, so H can go here, and it will be stopping this radical, okay, and then this bond for the unpaired electron here is will be making a double bond here. So both of the radicals is now stop, okay, and remove, or we can say no more polymerizations. So the difference between the disproportionations and the recombinations is that in disproportionations, these two molecules are not so similar, or is proportionally is not similar, but they will complete together. Okay, they will complete together. Compare with if we have these recombinations, they are having two similar monomer which has the radicals, and then they are going to combine, and these radicals become a bond. We call this as recombinations. But for these proportionations, we see that these two molecules is not so similar, or we could say it's disproportionate, but they are going to complete each other. They are going to complete each other. And then finally, both of methods will stop the polymerizations, and thus we have the final product. Okay. So that's basically the chain growth. We start from initiation, we propagate, adding monomers, and then we stop the polymerizations by terminations. So that's 3 steps to be completed. The 4th steps, actually, we can also have an alternative. If we want to transfer the radicals into another chain, which are it actually quite possible with some certain method. If we want to make sure that we want to adjust and tailor a specific polymer that has maybe many functional groups, then we need to transfer it to another chain. That is also possible. We are going to talk about the chain transfer, I think, on the next course. Okay, so I think I will end this video up until here, and we are going to continue later on. Okay, so I'll see you on the class.